Hello, in this video we are going to talk about inrush current of power factor capacitor bank because we hear a lot like this that capacitor deteriorates because of switching by electromechanical contactor. Then thyristor based panel shall be implemented. So we thought to share this video to understand how does this inrush current exactly takes place and how can we control by thyristor switching. This is an ideal circuit diagram of capacitor with a switch. This is a sinusoidal supply voltage, that is Vs. We know that Vs is equal to V peak sine omega d plus alpha. And then these are capacitor plates. As we know that the capacitor plates, one plate might be having a positive charge and one plate might be having a negative charge depending upon the voltage that is going to be applied on it. So Vs is a source or supply voltage, Vc is a capacitor voltage, Ic is capacitor current, plus and minus is charges on the capacitor, C is capacitance in farad. Okay, so we know that capacitor resists to change in voltage. That means it wants voltage to remain constant across it. So initially, if there is no charge on the capacitor, when we close the switch, we apply Vs across capacitor plates. So let's imagine and assume capacitor voltage Vc is 0 before switch is closed. At switch close, Vs, that is AC voltage, if it is at its peak value, okay, here at switch close, change in voltage is from 0 to peak voltage, that is 0 to maximum. Suppose if it is 415, so maximum would be in the range of 1.414 of 415, so maybe around 500 and 600 range. So this voltage difference is called a change in voltage. So we explain like this. Now capacitor resists this change in voltage, but now applied voltage is a peak value. So to resist the change in voltage means capacitor must attain this new voltage instantaneously. It will do so by exchange of a required amount of charges Q between its two plates and a capacitance value. So this means when it has to attain a new voltage, or let's say a peak voltage, then these plates must exchange those number of Q, that is charges, to attain the new voltage that is applied by the sinusoidal source. So there will be exchange of lot of Q to get a new voltage level. So that exchange of Q means the flow of charges, means a current for reaching a new voltage. So huge number of Q in a small time of interval will flow. Now this means a very high inrush current is generated. So let's understand this in some mathematical form. We know that Q is equal to CVC. Q is the charges on the capacitor, C is the capacitance, and Vc is the voltage across capacitor. So if you see this formula, this means Q is actually a function of Vc, that is voltage that is going to come across capacitor. This means Q will follow Vc graph. So whatever changes occurs in voltage, Q will follow the same. So if you take a derivative of both side with respect to time, so dq by dt is equal to C dVc by dt. So rate in change of voltage will be associated with rate in change of charges. So we know that rate of change of charges is nothing but a current. So we can write this I is equal to C dVc by dt. So now this explains the same. If dVc by dt, that is rate of change of voltage, is high, associated changes in charges will be high. That means the flow of Q will be high and thus current will be high. Now this flow of Q is limited by C, that is capacitance. So this is very basic logic, and due to this capacitor starting, it creates high inrush current. Now it is obvious to understand that if we want to start capacitor without high inrush current, we must see that change in voltage shall be zero. That is, capacitor must be started when supply voltage is equal to capacitor current, capacitor voltage. So we can have the rate of change of voltage will be zero at the starting. So when Vc is equal to X volt, then the switch must be closed that supply voltage should be also at X volt. So let's understand by this by graphs. Now this graph shows this is a voltage waveform. This is VR, that is apply voltage. This is current waveform, and this is a charge waveform. As I explained in this video, the charges behaves or follows voltage in capacitor. So suppose we start a capacitor at 0 volt, 0 volt of a supply waveform. Then we can see the charges also starts from 0 sinusoidally. It follows a voltage curve. So if we see, basically this is also a sinusoidal waveform of Q, and we know that I is equal to dq by dt. That is, I is actually the derivative of this sine waveform. So we know the derivative of sine waveform is a cosine waveform. So this is a cosine waveform, that is a current waveform. So if you see at starting from 0 time to the switch is closed at 0 voltage, the rate of change of voltage across the capacitor is 0, and as you see Q follows voltage, the rate of voltage is 0, so Q follows with 0 value, and Q follows with a 0 value. That means current is 0 when the switch is closed, and then after the switch is closed, it takes the value which is the steady state value. So it takes the steady state value. So we will find this kind of graph without any high inrush current when we switch the capacitor bank at 0 voltage, when capacitor initially has no voltage. So the Vc is 0 and Vs is 0. So the dVc by dt is 0. The rate of change or the change in voltage across capacitor is 0 at this point in time. Now suppose what happens if we start at peak of the voltage. Now as we said, we see that initial voltage on the capacitor is 0. Okay, now and we start or we apply the voltage at peak level, that is at maximum voltage level. So at this time, suppose the switch is closed, what happens is, if you see this line, it is actually a horizontal vertical line. Sorry, it's a vertical line. So the slope is a maximum at this particular thing on the graph. And as we discussed, the Q follows V. So the same sharp slope is seen in this Q waveform. So whenever there is a sharp slope is seen, that means I will be sharp, because I is actually the slope of Q waveform. So this happens when there is a huge difference between the capacitor voltage and the applied voltage. Now this is occurring, this is depending upon the capacitance value, depending upon the voltage level, the high inrush current or the inrush current is limited, okay, or can be decided. So if you see we do it at 30 degree, so it will be like this. So still at 30 degree, if you see this kind of slope, there might be a possibility that high inrush current will be seen. Now it is very obvious, if we want to switch it on at 90 degree, so it is very obvious that capacitor should also be having a voltage of 90 degree. So the Q at that point will be 0. Now I'll see, this is a very ideal conditions, but we'll see one of the graph that we have captured when capacitor starts at 0 voltage. So if you see, this capacitor has started at 0 voltage at time minus 0 to 0. This is a there is no inrush current actually, but in steady state the current is at peak, the current should be at peak when the voltage is 0. So it gets, this is a practically derived value, or this is a practical waveform of this. Now we'll see what happens in practical. Now in practical operation, there always exist series inductances and resistances. See this graph below. So whenever there is a capacitor we need to switch, there either may be a inductance of a source or a transformer, or there might be a series inductance that we put basically for harmonic filtering. We put 7% detuned reactors and all that stuff. So now we know that in VL, in inductor, VL is equal to L di by dt. That means, according to this, inductor resists to change in current, that it wants the current to be constant through it. Now as explained above, capacitor wants to exchange charges at faster rate to attain new voltage. Exactly opposite behavior is shown by inductor, and it tries to stop the exchange of charges, and it is done by self-inductance. Now this opposition is limited by L, that is inductance. So in this process, charges does not flow as required for getting a new voltage on the capacitor, and we see oscillations in current. I refer the graph below. So now we see even the voltage is no sorry, even in this particular graph, we got a 7% reactor in series with capacitor, and we started the capacitor at 0 volt, but still, because of the inductance being in series with capacitor, this oscillation is seen, and that is called transient oscillation. Why to have concern about this? We already at the start of the video we explained. As explained above, high inrush current flows, and this means higher local heating, and this damages capacitor's dielectrical strength, and capacitance starts deteriorating. Secondly, this current produce same oscillation in voltage of a common bus where other voltage sensitive loads are connected, and that is also damaging to the sensitive loads. Thank you very much for listening to our videos. Hope this will help you to understand the importance of capacitor switching.